Thank you. Like Morgan mentioned, this was a project that was done in conjunction with DFI, Berkeley Construction, USF, um, and Florida Department of Transportation. What we were looking at is implementing the thermal integrity system for use in auger cast piles. Thermal integrity is it's a quality assurance system that's widely used in drilled shafts, but not so much implemented in auger cast piles, at least in Florida, because in auger cast pile, it's not commonplace to install access tubes. And for that reason, auger cast piles aren't very much used in FDOT projects. I think they're restricted to pretty much just sound wall construction. So the purpose of this program was to look at implementing thermal integrity for auger cast piles. So we did some field modeling, did some lab modeling, and then did a full-scale field test. So this is auger cast pile construction, different than drilled shaft construction, obviously, in that it's a full fly auger that's penetrated full depth and then extracted while grout is put in. And because of that, construction is different. As opposed to drilled shafts, auger cast piles typically have either just a single center reinforcing bar or maybe a partial cage with the center bar that extends full depth. Quality control. This is why auger cast piles are not widely used on FDOT projects right now. While there is quality control during construction with automated readings from grout pressure, grout volume, penetration rate, post-construction quality control is somewhat lacking. This is an example here, and it's hard to see in this picture, but when you get to the surface and you're withdrawing the auger, if you lose grout pressure, you get a necking effect at the top of the pile. So yeah, this was our goal for the project. Yeah, I've already been over that. There was two phases. First, we went and did a bunch of numerical modeling, looked at past case studies, and then this part of the project was actually the field implementation. So what we did 7 test piles, and then there was also going to be load testing done on these. There was 2 compression piles, 2 tension piles, and 2 laterally loaded piles, and then 1 pile that was to be extracted for evaluation. And then each pair of either compression, tension, or laterally loaded piles, there was 1 18-inch and 1 24-inch. Lengths were between 40 to 60 feet. This is the layout. This shows each of the 7 piles. The extraction pile off to the left, and then each pair of compression, tension, and lateral piles off to the right. And then the other piles in between are reaction piles for the load test. And then this is the reinforcement that was used. Each of the tension piles and the extraction pile had a 3-inch threaded Williams form bar. And then the rest all had the compression piles had partial length cages, and the extraction pile had yes. The extraction pile had a full length center bar and a partial length cage. This is a picture of the 2 compression piles. Because they had a full cage, we installed access tubes. With one of them, we installed steel access tubes. The other one was PVC access tubes. And then the yellow wires, those are the thermal wires that were installed on both of them as well. And then this is C1 and L1. This is the two 18-inch piles, compression and lateral. They did not have access tubes. They were just instrumented with wires. And this is the extraction, which had just wires, but it had cage wires and a center bar wire. And then these are the center bar wires for the tension piles and yes, and the tension piles. These are just pictures of construction. This is done in Central Florida. Typical auger cast construction using Berkel's equipment. And then after construction, we did probe testing. And we went in, we did it on 3-hour intervals. I'm sorry, 6-hour intervals. 6-hour intervals, so we tested overnight and into the morning. There's a picture of the testing setup. It's an automatic system that lowers the probe down and then reels it back up. And this is in the morning, where it's a little bit easier to see. The blue wires up at the top, those are the strain gauge wires for the load testing program. And this is a look at the results from probe testing. On the left, you can see at 6 hours, very little heat had started to be generated. Peak temperatures came at around 12 hours, and then at 18 and 24 hours, it drops back off. And then the graph on the right shows a comparison among tube temperatures. One thing to note on the graph on the right, at around 20 to 25 feet, the eccentricity between tube 1 and tube 3 indicates cage offset. This is the wire system for the 24-inch compression pile. And we did have, in this case, some wires fail, which is it's one of the downsides to the wire system as opposed to the probe system. These are the two tension piles. This is the extraction pile with wires instrumented. And this is the temperature profile from the extraction pile, from the extraction pile. It was actually very, very normal. It was probably the most uniform of any of the temperature profiles. Okay, so when we went to do data analysis, there were a few things we wanted to look at. Comparison between wire and probe data. Comparison between taking cage measurements versus center bar measurements. And one of the last things is what we call the T-soil or the T0 method, which is when we do a temperature to radius conversion, whether we take the intercept of that line back to T0 or what we call soil temperature. So here's a comparison of probe and wire data. The blue curve being wire data from one of the piles, and then the red dots being those 6-hour intervals from probe testing. These are comparisons of tube and wire data from temperature profiles on, I think, either L1 or L2. No, this would be from C1 or C2. But it shows that both probe data and wire data were virtually the same. And one of the things, if you look at the graph on the right, this is, again, comparison of center bar data to cage position data. And center bar data should always be warmer than cage location. So one of the things we noticed that on L2 in the graph on the right is where the cage temperatures were for some reason warmer than the center temperatures. And so initially it threw us for a loop, but we did some modeling and showed that, yes, if the center bar is offset all the way to the edge of the cage, and if it's in between two of the cage locations, then yeah, it can be warmer. And we suspect that's what happened. Because if you notice at the top of each of these profiles, the blue line is, the difference between the blue and the red line is much greater than it is at the bottom. So at the top, where you have a better ability to center that center bar, at the bottom, it was likely offset to the edge. And then same thing here. From about 20 feet down, you see that the dashed line, the center bar measurements, become very close to the cage measurements. And then one of the things that might be attributing to this is the centralizers. The centralizers were very minimal, I think spaced at 10 feet. So it's possible that the use of more robust centralizers and greater spacing, or less spacing rather, could help with this. This is the extraction pile, similar situation. You can see that above about 20 feet, the cage measurements are much less than the center bar measurements, and then down below, they come together. All right, so those are all qualitative type analyses. To do a quantitative analysis, we go to temperature to radius relationship. So what we looked at was different ways to do this analysis. One is the hyperbolic temperature to radius relationship. The other is the linear temperature to radius relationship. And then we have to look at the input parameters, which are how much volume of grout was placed, local soil temperature, and time of testing. So this is kind of a convoluted graph, but it shows the difference between the hyperbolic, which are the curved lines, the hyperbolic temperature to radius relationship, and the linear temperature to radius relationships. And you can see that for larger shafts, in the area where the red dots are, the linear and the hyperbolic are very much in line, but for smaller shafts, it tends to overpredict. And this is a case of that. This was actually from a previous study, 24-inch shafts, and they were extracted and measured. And the dashed lines are actual shaft dimensions. And then the black lines are using the T0 method. And then the red line is using the T-soil method. So for these linear approximations, instead of bringing back those intercepts to the 0, point, we bring them back to whatever the local soil temperature is. And you can see that it fits the actual shaft shape much better. These are pictures of the extraction pile. It was actually a pretty good looking pile, no real anomalies. This is the radius conversion for the extraction pile compared with the actual measurements. After we extracted the pile, we went back and measured it on 1 foot intervals, which are those blue lines there. We measured it multiple ways. We did circumference measurements, then back calculated radius, and then we also had a large caliper that we used to measure diameter. And after doing the analysis, it was very similar to what the physical measurements were. On the other hand, this is a comparison with the automated DAC logs. And the blue line is, well, from the automated logs and from manual logs. The blue line is the automated data acquisition logs, and the red line is the data from manual logs. And this is the radius using the volume from those logs. And one of the problems that we had was determining what volume of grout to use, because when doing this analysis, you have to know what volume went into the hole. And then the thermal data will tell you how that volume was distributed. So we know how much volume was pumped, but then once grout return happens, how much volume is displaced, how much volume is used to fill the lines. So that was one of the issues that we kept on over-predicting. This is a comparison of different methods of determining the volume. We tried taking total volume, obviously an over-prediction because it's going to be grout return. We did total volume minus the initial pump count, total volume after the volume after return was noted in the logs, and then we tried total volume after return was noted in the logs, then added back in the volume of the auger itself, assuming that it was still filled with soil. All of them were over-predicted. So summary, probe and wire measurements were virtually the same. There is, of course, pros and cons to both. With wire measurements, you get continuous data through time, but then you also have a certain amount of wire failures. And then once you have that, there's no way to recollect that data. With probe data, you don't have that, but you only have one point in time where you can collect that data. Center bar and cage measurements showed similar features, but one of the problems was center bar alignment. We were only able to see that when we had center bar and cage measurements together. If you have just center bar measurements alone, there's virtually no way to detect that misalignment. And then from an analysis standpoint, the T-soil method we found works well for smaller diameter shafts, or what's typically in the range of an auger cast pile, the 24-inch range, as opposed to with larger diameter shafts where the T0 method works better. And conclusions. Conclusions we came from this was that for construction, center bar alignment should be improved by using more robust centralizers and possibly a more frequent spacing. And then also with volume measurements, it's crucial to using the thermal integrity analysis method. So there should be good judgment used in predicting the actual volume of grout that goes into the hole. Acknowledgments. I'd like to acknowledge everyone at Florida Department of Transportation, David Horhoda, Juan Castellanos, Larry Jones, Morgan Neesmith at Berkeley, and not listed on here, but Dr. Gray Mullins at the University of South Florida, and of course everyone at DFI that helped with the project. And that's it. Thank you.